Hi, my name is Hansu Kim, and today I will be presenting edge-based procedural textures, a new interactive inverse procedural approach for example-based texture synthesis. Texture synthesis has been used in many computer graphics areas, such as digital art, gaming, real-time applications. Its goal is to provide easy and expressive methods to generate textures. Existing approaches can be classified into three major categories. 1. Example-based methods. 2. Procedural synthesis. 3. Simulation-based methods. Example-based methods use existing textures to create new ones. Usually, the results are limited to the provided inputs, and it doesn't provide a flexible user control. Machine learning-based methods are more recent and advanced techniques, but it requires a large set of training data that also need long training time. Because of its nature, the result of an ML-based method is also subject to the training data, and it's usually hard to fine-tune the model. Inverse procedural modeling has its advantages in that it finds descriptions of design processes in order to generate new shapes or textures. It's similar to example-based methods, but the key difference is that inverse procedural approaches find the underlying representation of the input. It has been successful in generating regular patterns, noise-like shapes, and well-defined structures. But for semi-stochastic objects, whose structure is subtle and unclear, the studies are limited, mainly because of its complexity. Thus, semi-stochastic shapes cannot be easily represented by noise functions or curves. So it's extremely difficult to define a good procedural representation for those semi-stochastic shapes. We introduce an example-based inverse procedural texture synthesis method that fills the gap between example-based method and inverse procedural modeling. Our key observation is that example-based texture synthesis can be expressed as a controllable inverse procedural problem, especially for semi-stochastic textures that we cannot clearly define important visual features. We focus on edges that play a major role in human perception. Edges define visually important features in those semi-stochastic textures, and those features can be stored as a parameterized procedural building blocks. The concept is described in the picture. We extract edges from the inputs, classify them, and build a parameterized procedural model. Users can interactively synthesize using building blocks in the model, or they can simply use an automatic synthesis. The picture shows an overview of our system. The input is a two-dimensional texture, and it firstly goes to the texture analysis stage. Edges are extracted and grouped based on their properties. We then do an additional group property analysis to finalize the building blocks. Texture synthesis stage is similar to an example-based method, but we use our procedural model to synthesize the output texture. The user, or a fully automatic system, selects desired edge groups and places them on the output image. Then our system fills the pixels between the edges and edge groups. The entire process is fast and lightweight, so the user can immediately see the result. We will discuss individual steps from the next slide. In texture analysis stage, we first find the edges by using the structured forest edge extraction algorithm. Then we apply a few pre-processing steps. First, we thin out the edges in order to get the skeleton of each edge. That way, we can count the number of pixels as the length of the edge. Second, we do a principal component analysis (PCA) using the skeleton pixels to find the center of the edge and the first eigenvector. Lastly, we calculate the angle and bounding values of the edge to define the feature vector. Our feature vector has four main properties from the analysis: length, center, angle, and the width. That way, We can parameterize edges and classify them into bins in a histogram. The picture shows an example. X-axis is the relative length of edges. 1 means the longest edge is length in the input texture, so the left bin means lower 33% in terms of the length. Y-axis represents the angle of each edge. So the top right bin shows longer edges whose angles are between 120 degrees and 180 degrees. Then, we group edges to make a procedural building blocks. We use the superpixels as the blueprint of the edge groups because it shows visually similar regions, which is a good starting point. We then group edges whose centers are in the region boundary. Then, we perform an additional analysis using the blueprinted groups. We use PCA again to get the group centers and calculate the spatial distribution of each edge in the group as shown in the left picture. We can classify edge groups in the same way as shown in the right picture. This way, we can characterize a group independent from individual edge. For example, a horizontally long edge group can have many vertical edges. Our two-level hierarchy helps us distinguish the two different styles. The next stage is texture synthesis, and it has two major steps: edge group placement and pixel filling. In the edge group placement step, we select edge groups and place them in an empty image. We call it a canvas. The edge groups will be a sketch of the output image. This process can be done interactively or fully automatically. In interactive mode, the user manually selects and places edge groups directly. In the automatic mode, edge groups are automatically placed based on the preset procedural rules. This is an example of the interactive mode. The user selects their interested edge groups from the input, then places it on the canvas. The selected part will show off in the output image. This is an example of the automatic mode. Let's say we define a design rule that only allows long edges on the top of the output image. The system will automatically choose edge groups based on the given length and the angle. After edge groups are placed, our method automatically fills the gap between edges. We use a seamless image cloning for a pixel filling process. It's a simple but very fast method that enables our interactive editing. The picture shows an edge group and its pixels rotated in the output image. The complexity of our method depends on the input size and the number of extracted edges. It grows linearly, so we can easily produce large textures. Our method takes less than a second to synthesize the output of 2K by 2K pixels with 360 edges. We compare the performance of our implementation with image melding, and the results are shown in the table. Because our method does not require any exponential algorithm or heavy repetitions, it's very good for an interactive application. For the input texture of 1K by 1K, our methods took almost 0.2 seconds, which is more than 3,000 times faster than image melding. This picture shows an example of large texture synthesis. The size of the output texture is 2K by 2K. Edge groups are manually selected and placed by the user. This is another large synthesis result using multiple input images. The picture shows blending and the transitions between two examples. The various angular structures were generated by rotating edge groups in the top input. This result shows fully automatic texture synthesis. The red marble texture was analyzed and translated into our edge-based procedural model. Then, the algorithm automatically selects and distributes edge groups based on given rules. The rules can easily be controlled by parameters. The left image shows a random distribution. The center image is angled synthesis, and the right image shows region-based distributions. we compared our method to noise-based methods. The images in the left column were generated by Gabor noise-based approach. The images in the middle column were generated by local random phase noise method. The right column shows our results. Those two methods were effective for stochastic images, but they were not suitable for semi-stochastic textures. The left column shows the semi-procedural textures, and the right column shows our approach. Our approach allows an interactive synthesis using arbitrary stationary features, which is edge groups, and it is 60% faster using only CPU. Our method is not designed for textures with well-defined structures, and it needs enough number of edge groups placed in the output texture. If those conditions are not satisfied, then it makes undesired artifacts as shown in the picture. In this picture, both of the inputs have clear and strong patterns, and only two edge groups were provided in the output. Our method generated blurred, abrupt transitions because of the lack of information. This is a comparison between our method and the self-tuning texture optimization. The given example is very small, and it has strong structural properties. Our method could produce blurred or unclear boundaries between those structures. Plus, it might also fail if there are no clear and long edges in the input. The bottom row shows the failure case where our method fails to capture visually salient features from the input. We introduced the edge-based procedural texture synthesis method that effectively captures visually salient features in semi-stochastic images. We use the edges as the building block of our procedural model. Our procedural model provides users with an interactive and flexible way to synthesize larger textures. Our system also provides full automatic synthesis by taking advantage of the procedural approach. There are several options for possible future work. In this work, we only use the one level of superpixels. We could use the idea of a hierarchical approach to manage our edge groups in a hierarchical way. Adding more visual features would be very interesting. We can define a new texel using our approach. Finally, we could build a design system in combination with machine intelligence. This is the end of my presentation, and thank you very much for your time. I would appreciate any questions or comments.